Alrighty, how is everybody this morning? Hanging in there? Okay. All right, cool. So today we're going to start with a review of series. So last time we talked about series circuits. We said that a series circuit is when you have components connected end to end with nothing in between. So we'll go over that definition again. We'll talk about how we found resistance for a series circuit, and then how we used Ohm's law in series circuits. And then we'll go over some metric conversions. Remember, we used engineering notation to describe very large or very small numbers without having to write tons of zeros. So, and you guys have hopefully been working on some homework about that. So I will go over that and maybe even do a homework problem on the board. So one less for you to worry about. And then for the lecture today, I'm going to talk about parallel resistance. So first of all, we'll talk about what is parallel and then why we care about that. And then the basic idea of parallel resistance. And then we'll do some calculations to actually figure out resistance values in parallel circuits. And then we'll do an example from the homework for today. So for today, I'd like you to work on the calculator practice homework on page 89 and 90 in your lab book. And then I will do an example of that. And then we'll go on and do the preview for today's lab. So in the lab today, you'll get to work on multisim. We're not going to have a hands-on portion of today's lab. Today we're just doing multisim. Next time we'll continue working on parallel circuits and we'll do a lab that's all hands-on. Okay? So we kind of broken it up between these 2 days. So that's what we'll be working on today. So any questions before we get going? All right, cool. So then let's review series circuits. So we said that components are in series if they are connected kind of like this. So the end of one component is connected to the beginning of the next with nothing in between. Connected end to end with nothing in between. So we said that the shape of the circuit doesn't matter as long as it matches this definition. So we could have a circuit that's shaped like this. You know, it's got a crazy bend in it. Is that series? Yeah, it's series because there's the one component is connected to the beginning of the next component and there's nothing in between. So that's in series. You could have components like this. Those are they in series? Yeah, those are in series because the end of one is connected to the beginning of the next with nothing in between. So that's also in series. But if you have components like this, those are not in series because you have something connected in the middle between them, okay? So series is when you have components connected end to end with nothing in between. So then we talked a little bit about series resistance. And we said that resistance is pretty easy to calculate in a series circuit. What do you have to do to find the equivalent resistance for a series circuit? Yeah, you just add the values together. So if you have a 100 ohm resistor and a 300 ohm resistor, we could say that that is equivalent to a single resistor that is what value? Yeah, 400 ohms, exactly. That means that if you took a meter and you connected it here and here, you would measure 400 ohms. Another way to think about it is that if you had a black box and all that was sticking out was the two wires on the ends, and you had, say you had two black boxes, one that had a 100 ohm and a 300 ohm resistor connected in series, another one that had just a 400 ohm resistor in it. If you just measured their resistance, there'd be no way to tell which was which. They would appear exactly the same on the meter, okay? So that's how we calculate resistance in series. The equivalent resistance is the sum of the individual resistances. So any questions about that? Okay. And then we did some Ohm's law with series circuits. So we tried to use Ohm's law to figure out the voltages and currents for series circuits. So let's do another example of that on the board. So let's say we have a 20 volt power supply here. And let's say we have a 3 kilo ohm resistor and a 7 kilo ohm resistor. And we want to figure out kind of everything that we can about this circuit. So we'll call this one R1, this one R2. So we want to know the total voltage, the total resistance, the total current, and then the voltage for each resistor and the current for each resistor. So let's see how we can figure that out. So first of all, do you see anything up here that we can write down without having to do any calculations?
The total resistance?
Almost. Yeah, the total voltage. The total voltage is just the voltage that's coming from our power supply. So in this case, that is 20 volts. Now, yeah, the next place I would go is the total resistance, because we don't have to do much for that, right? So first of all, we have to look in the circuit and ask, are these resistors in series or not?
Yeah.
Yeah, they are, because they're connected end to end with nothing in between, okay? So these resistors are in series, so to find the total resistance, we say R total equals R1 plus R2. So in this case, that's 3 kilo ohms plus 7 kilo ohms. So that is 10 kilo ohms. So that's the total resistance. Okay? So we can redraw this circuit using that equivalent resistance. So we can say that this, we still have a 20 volt power supply here. And then over here, instead of drawing two separate resistors, we can just draw one with that equivalent resistance. So this, we'll call this one R12 because it represents the combination of those two. And we'll say that that is 10 kiloohms. Okay? So any questions about that so far? Nope. All right. So then the next thing, what would be the next thing that we could look at? Sometimes that's the hardest part of these problems, is figuring out what to do next. So what would we do next once we have this? Yeah, that's a good idea. We can find the current. We know the voltage, 20 volts, and we know the resistance, so we can find the current. So what law would we use for that? Ohm's law, that's right. So, so what we can do is we remember Ohm's law is like this. We've got V, I, R, that's right. And here we're trying to find the current, so we write down I equals, we cover that up, we see it's V over R. So then that, what is our voltage in this case?
20.
Perfect. 20 volts. And then our resistance? 10 kiloohms. So I just do 20 over 10. That gives me 2 amps, right?
It is in kiloohms.
Ah, kiloohms. That's right. Ah, right. So it looks like I can just divide 20 by 10, but yeah, this is kilo. So we need to convert that to regular ohms before we do our math. So this is a little bit of that metric conversion we worked on last time, right? So this is now 20 volts over 10, and kilo stands for 1,000. So that's 10,000 ohms. So you should always put your numbers into raw units like volts and ohms before you do your calculation. Get rid of any kilo or milli or mega or anything like that. Just make sure it's all in raw units, and that way your answer will come out in raw units. So 20 over 10,000 is 0.02 amps. And then once you have that in raw units, then you can convert it to something that's more convenient. So you're right. Yeah, it is 0.002. Thank you. So 0.002 amps. So then we can convert that to milliamps. So that comes out to be 2 milliamps. Okay? So that's our total current. 2 milliamps. So any questions about how we got that? All right. So that's the current that's coming out of our power supply. That's what total current means. That's the current coming out of our power supply. So that's 2 milliamps there. And how much current is flowing back into our power supply? 2 milliamps, that's right. It always has to be the same as the current flowing out. So that's also 2 milliamps flowing back in. All right, so then how much current do we have flowing out of the power supply in this circuit over here? 2 milliamps, exactly. They're the same. These are equivalent circuits, so the current coming out over here is going to be the same as the current coming out over there. So then we have 2 milliamps going back in as well. So then how much of that current comes down here through R1?
2 milliamps.
2 milliamps, exactly, because it has nowhere else to go. Remember, current is like the water flowing through a pipe. So this is like 2 gallons per minute flowing along here. And this is like one long pipe. So if you have 2 gallons per minute here, you better have 2 gallons per minute over there because the water has nowhere else to go. It just flows along there. So then how much of it goes through R1? 2 milliamps. And how much through R2? 2 milliamps, that's right. Because again, the current only has one path that it takes. It can't go anywhere else. So it all has to go through there. So you get 2 milliamps going through both of those, okay? So then, can we write down any more answers over here?
Yeah, I1 and I2 is 2 milliamps.
Exactly. These are both 2 milliamps. That's what we just figured out right there. So, any questions about how we got that? Yeah.
Right. On the homework, I'm kind of confused what you want us to do in terms of value and exponents. Is that just like
Okay, so we'll go over that in just a second. But let's finish up this problem first. But yeah, we'll go this homework. Yeah.
Yeah.
Yeah, we'll go over that a little bit later in the lecture. I'll get to that down here. So don't forget about that, but I'm not quite ready for that yet. Yeah, other questions about this part here? Okay, so then what are the last two things that we have to calculate are V1 and V2. So how can we figure those out? Yeah, exactly. Ohm's law again. Yeah. So we're trying to find the voltage. So we can say V equals, we cover that up. We see that it's I times R. So let's do the first one first. So what is I here?
2 million.
Yep, 2 milliamps. And then R, what do we have?
3 kilo.
3 kilo ohms. So we can convert those into raw units again. So that becomes 0.002 amps times 3,000 ohms. So, yep, 6 volts. So that's our voltage across R1. Remember, a voltage across a component means the voltage difference from one side to the other. So that's 6 volts right there. And then we can do the same thing for R2 down here. So we can say V equals I times R. So what is I here? Exactly, 2 milliamps. And then R, 7 kilo ohms. So that is 0.002 amps times 7,000 ohms, and that comes out to be 14 volts. So we have 14 volts down there. Okay? So questions about that?
Professor, like if we have one source 20 volt, like if you found one of those voltages, can we like write it equation like 20 volts equal 6 volt plus V2 or V1?
Yeah, that's right. So that's a great observation. So you see, yeah, over here we have a 20 volt power supply, and you'll notice these two voltages add up to 20 volts. And yeah, that's not a coincidence. That will always be the case in a series circuit. The two, or however many voltages you have, they'll add up to the total voltage in a series circuit. Okay? So yeah, so if you found the first one using Ohm's law, and you knew that was 6 volts, you could say the other one has to be 20 minus 6. It has to be whatever the difference is between this and 20. So these two together add up to 20. Yeah, so that's a great observation.
V total equal V1 plus V2.
Yeah, exactly. Mm-hmm. Yeah, perfect. All right, so when we're looking at this series circuit, I want to point out another thing. So in series, the currents, can you have one current in R1 and a different current in R2? No, exactly, because the current from R1 just flows directly into R2. So in series, the currents are all the same for all the components. But what about the voltages? Do we have to have the same voltage on R1 and R2? No. So the currents are the same, but voltages may be different. Could you have a series circuit where the voltages were the same across each of the resistors?
We can make it like we make equal resistor.
Yeah, exactly. If they were all the same resistance value, then the voltages would all be the same. So it's possible that you could get the same voltages, but you can also have different voltages. So the currents have to be the same, but the voltages may be different. Okay? So that's for series circuits. So any questions about that? Okay. All right, so we talked about what series is. We did resistance calculations for series circuits. We talked about Ohm's law. So then let's go on and do some metric conversions. So this was the homework that I assigned last time, was to take a look at some metric conversions. So these were in your lab book. I wanted to say, so page 61 in your lab book. So did anybody have one of those that was particularly challenging you might want me to take a look at on the board? Page 61. So remember we had this line, we had units, and then kilo, mega, giga, and then milli, micro, nano, and pico. Anybody have one of those problems that was especially hard? You want me to take a look at? Or I'll just pick one at random. All right. How about number 6, 1500 kilohertz to megahertz? So we're looking at 1500 kilohertz, and we want to convert that to some number of megahertz. So we said that the way that this number line works is that each place on the left is 1,000 times bigger than the thing to its right. So kilo is 1,000 units, mega is 1,000 kilos, giga is 1,000 megas, and so on. And so what that means is that if you're moving from one spot on the line to the next place left, you need fewer of these things because these are bigger. So if you're moving to the left on the line, you actually divide your number by 1,000. So every spot you move left on the line, you divide by 1,000. And a quick way of doing that is to move the decimal point 3 places to the left. So, so here, we're going from kilo to mega. So how many spots am I moving?
3.
Yeah, I'm moving 1 place left on the line, which is, 3 decimal places. When there's no decimal point shown, like here, it's just 1,500. It doesn't show a decimal point. That decimal point is assumed to be at the end of that number, okay? So that's where it is. So then we move 3 places left from there. And so that gives us 1.5 megahertz. So 1,500 kilohertz equals 1.5 megahertz. Okay? So are there questions about that? No? Okay. So please work on that for homework, and please finish that up when you get a chance. That assignment, like all the other assignments, is due just by the end of the semester, okay? So if I were you, I'd work on it now and get it out of the way so you don't have to think about it anymore. But as long as you turn it in sometime before the end of the semester, you will get full credit, okay? All right. So then let's go on and do our lecture for today. So today we're talking about parallel circuits and parallel resistance. So what is parallel? So elements are in parallel when they're connected like this. So you could think of it as being kind of side by side. Yeah. So if you wanted to write out a definition, you could say that the beginning of each component is connected to the beginning of every other component. And the ends of all components are connected to each other. So that's what it means to be in parallel. So you can see that the beginning of all of these components are connected to each other, and the ends of the components are connected to each other. So as long as there's a wire going from one thing to the rest, that shows a connection, okay? So these components are all in parallel. So questions about that? All right. So then, so why do we care about this? Well, again, we care because many circuits in the real world are wired together in parallel. So remember last time we talked about old-fashioned holiday lights. And we said that they were wired together in what? In series, exactly. So with old-fashioned holiday lights, you had a little bulb like that, and then that was connected to the next bulb, and then that was connected to the next bulb, and so on. But there was a problem with the old-fashioned lights, right? What happened if one of those bulbs went out in that string? Yeah, they all go out, exactly. And hopefully, when we look at this, we can start to see why. Because these are all wired in series. So any electricity that is flowing through this circuit has to go through every single light bulb. And if one of these is broken, then the electricity stops, and it can't flow around. So it can't go through any of the other light bulbs. It can't get back to where it started. So the whole thing stops. All right. So that was a problem with the old-fashioned holiday lights. But New holiday lights don't have that problem anymore. You know why? That's right, they're wired in parallel. Exactly. So new holiday lights are wired like this. So you have your power supply here, and then you've got these long wires, and your holiday lights go in between. So you have one there, and then one there, and so on, like that. And so now what happens is that if one of these lights breaks, say this one goes out, well, the electricity can't flow through that one anymore, so that one goes dark, but the electricity can still flow through the other ones. It can go through there and come back. It can still go through there and come back. And it can go through all the other lights, okay? So that's why these new lights don't go out if one of the bulbs burns, okay? The rest of the bulbs can still work. So in this case, a parallel circuit seems to be a much better way of doing this, okay? So that's one example of a parallel circuit, but there are many other examples of parallel circuits too. You could have speakers that are wired in parallel for a sound system, or other things like that. And in addition, many circuits include some parallel elements. So even if the whole thing isn't in parallel, some parts of it might be in parallel. So it's really important to understand how parallel circuits work so that we can design our own circuits and also understand other people's circuits. Okay? All right. So then let's play another one of those games where, like last time we looked at a circuit and tried to figure out if it was in series. Let's do the same thing for parallel circuits. So we'll play the is it in parallel game. All right. I'm thinking about starting a TV show. What do you think? No? Okay. All right. So we got our power supply here. And let's say that we have a component here, and then actually, let's not have the power supply yet. We'll have a resistor there, and then resistor there, and a resistor there. And we'll connect them together like that. Are those in parallel? No, exactly, because what are they? Is there another way of saying what they are? They're series, exactly, because the end of one is connected to the beginning of the next. So these are in series, not parallel. Even though they're kind of side by side, the connections show that they're actually in series, okay? What if we have resistors like this? Oop. Are those in series or parallel?
Yeah.
Those are in parallel. That's right. Because the ends are all connected together, and the beginnings are all connected to each other. Okay? So even though those components are in a line, they're actually in parallel. Okay? What if we have resistors like that? Are those two in parallel?
series.
Yeah, actually, right, exactly. These are all in series. What if I go like that? Are these two in parallel now?
Series.
Yep, they're still in series. Because the end of one is connected to the beginning of the next. So even though these two are kind of side by side, they look a little bit like parallel. They're not, because this other one is in between them. Okay. So those are a couple of different examples. So really, the thing to remember about components being in parallel is that the ends of all the components have to connect to each other, and the beginnings have to connect to each other. Okay? Did you have a question?
Actually, yeah. I think a good way to figure it out is that if you like one of the components die, would the circuit still be completed?
Yeah. So that's a good way to think about it. If one of the components burned out, would the electricity still be able to get to the other ones? Yeah. Mm-hmm. Yeah. Other question? Yeah.
It also depends where the power supply is. So if we connect the opposite sides.
Yeah. So right. So yeah, we'll. Yeah, when we start to add the power supply in there, it adds kind of another layer. So, and we'll talk more about that next time. Parallel circuits are a little bit trickier, I think, to understand than series circuits. So we're going to spread out our learning about parallel circuits over 2 classes. So today we're going to talk about what they are and how to find the resistance. But yeah, we'll save Ohm's law and the power stuff for next time. But yeah, it's a good point. So any questions about what is or is not in parallel? Okay, so then let's go on and talk a little bit about the idea of parallel resistance, okay? So parallel resistance. So the idea is, imagine you have 2 resistors in parallel. And say they're each 1,000 ohms. But now you want to find the equivalent resistance of these 2 in parallel. What happens? Well, what happens is that the electricity was coming along through here, and now it has 2 paths that it can take. So some of it can go that way, and some of it can go that way. Okay? So when we looked at series resistance, it was kind of intuitive to understand what happened. When you had resistors in series, the more resistors you put in a row, the more resistance you had. It kind of made sense. The more resistors you have, you just add up all of their resistances together to get the total resistance. Okay? That kind of makes sense, I think. But it turns out that with parallel resistances, the more resistors you have in parallel, the less total resistance you have. Now, this sounds kind of weird, right? You have more resistors, but you get less resistance? That always kind of took me a minute to wrap my head around. But let me try and explain what's going on. So basically, when you have more resistors in parallel, you're giving the electricity more paths that it can take. And so it can spread itself out. And so since it has more paths that it can take, it's easier for it to move. You could think about cars going down a road. If you've got a whole bunch of cars on a one-lane road, you might have a lot of traffic. But then if that road suddenly opens up and becomes a 6-lane highway, suddenly it's a lot easier for the traffic to flow, right? The same thing here. We're like adding more lanes for the electricity to move through. So it makes it easier for the electricity to flow. You could also think of it like water flowing through a creek. So if all the water is flowing through one narrow creek bed, it's going to have kind of a hard time. But then if that creek suddenly comes to a junction and splits off, and now you have 2 or 3 or 4 different little streams for the water to flow down, that water is going to have an easier time moving through those multiple paths. So the same thing is happening with resistors. If you have just one resistor, then all of the electricity has to go through that resistor, and it's kind of difficult for it to move. When you give the electricity multiple paths to take, it becomes easier. So in parallel, when you have more resistors, the more resistors you have in parallel, the less resistance you have overall. Okay? So that's the general idea behind parallel resistance. That's the big concept there. The more resistors you have, the less resistance you get. So questions about that? Yeah.
Which means if you didn't have resistors, the more lanes you have, the easier, the less resistance you would have. Like if you had no resistors or just the wires themselves,
Right.
the total resistance would just decrease. So the bigger the wire, the less the resistance. Right?
Yeah, that's true also. Yeah, so if you have a wire and you're looking at it on end on, and it's just a little tiny wire like that, then all the electricity has to flow through that wire, and it's going to have kind of a lot of resistance. When we're doing problems up here on the board, we treat wires like they have 0 resistance. And that's a good approximation, but in the real world, nothing is perfect, and even wires have their own resistance. So yeah, a narrow wire like this will have some resistance, and the more cables or the more filaments, strands of wire you put around that, the less resistance you'll have altogether. Or just the bigger you make that, yeah, the less resistance you'll have altogether. So yeah, that's a good point. Thank you. Yeah. So that's the general idea. The more paths you give the electricity, the easier it is for it to flow, and the less resistance it has altogether. So if we're talking about resistors in parallel and all of the resistor values are the same, then we can just divide one of those resistance values by the number of resistors, and that will give you the equivalent resistance. So if we have 2 1,000 ohm resistors in parallel, we could say that the equivalent resistance is 1,000 divided by 2, or just 500 ohms. Okay? If we had, say, a circuit where we had 3 resistors in parallel, 600 and 600 ohms, and another 600 ohms, then the equivalent resistance would be one of those resistor values divided by the number of resistors. So that would be 600 divided by 3. So that gives you just 200 ohms. So in parallel, when all resistors have the same value, the equivalent resistance equals one resistor divided by one resistor value divided by number of resistors. Okay? So, questions about that? And another thing about parallel resistance, so no matter what, the total resistance is going to be less than the smallest single resistor. So that's for all parallel circuits. So, any questions about that? Yeah.
So having like 10 resistors would be equivalent to having just one of the 10, basically, in terms of resistance. Is that what it's saying?
No, not quite. So if you had 10 resistors, so let's say you had 10 resistors and they're all 1,000 ohms. Seven, 8, 9, and 10. And each one of these is 1,000 ohms. What would be the equivalent resistance for that circuit?
Divided by 10.
Yeah, that's right. It's one of those resistor values divided by the number of resistors. So that would be, yeah, 1,000 divided by 10, which is 100 ohms. So this would just be 100 ohms. Does that make sense? And you might think, okay, well, nobody would ever do this, right? If you wanted a 100 ohm resistor, you just buy a 100 ohm resistor, right? But actually, sometimes people do make a circuit just like this. In fact, I saw an article about making this kind of circuit in a magazine not that long ago. And the reason is because when you have a single resistor, all of that electricity has to go through that resistor, that one resistor, and it really heats that up a lot. When you have all of these resistors in parallel, that electricity can spread out between them and can, it spreads the heat out over all these different locations. So that's what this article was about. It was somebody was making what's called a dummy load for a radio. So normally radios are connected to an antenna, and that antenna broadcasts your signal out to the world. But when you're just hooking up your radio and testing it out, you don't necessarily want to broadcast those test signals to everybody. It would be annoying, and sometimes the test signals aren't calibrated right, and they might be on the wrong frequency. You could be getting in other people's way, stuff like that. You want to have, so you might think, well, just disconnect the antenna. But it turns out that radios don't work well if their antenna is disconnected. The signal that was supposed to go out into that antenna actually bounces back and goes back into the radio itself and can overheat components inside that radio and damage or destroy your really nice, expensive radio. So you need to have something hooked up So the signals have somewhere to go, but you don't want to broadcast them out. So what people do is they use something called a dummy load, which is basically just a big resistor that's not an antenna. So it absorbs the signal without broadcasting it out. So this is the type of circuit that person built. They had like a paint can that had a whole bunch of resistors inside, and then it was filled up with oil. So when those resistors heated up, the oil dissipated that heat, and they didn't get too hot. And also you had 10 or 20 resistors all in parallel, spreading that load and that heat around so that no one component got too hot. Okay? So that's another example of where parallel circuits worked. And they needed to use parallel circuit math because they knew that dummy load had to have a resistance of 50 ohms. And so they wanted to have a final resistance of 50 ohms. And so if they knew they wanted to use 100 or 10 resistors, then each one would be 500 ohms because 500 divided by 10 would give you 50. Okay? So this is something that could be used in the real world. Okay?
And resistance changes when it heats up.
When they heat up? Yeah, it can a little bit. But yeah, I think that this person picked resistors that are relatively tolerant to heat changes, so it didn't change very much. Yeah. All right, so that's how we find equivalent resistance when you have resistors in parallel and they're all the same value. But what if they're not the same value? Well, if they're different values, then we have to use a separate formula, and we call it the parallel resistance formula. I know it's super creative, but they had to come up with some name. So this is what we use when they're all the same value. But when resistors have different values, we say that R total, the total resistance, or the equivalent resistance, let's just write it out. Equivalent resistance equals 1 divided by R1 plus 1 divided by R2 plus 1 over R3, and so on, for however many resistors you have. Okay? So let's do an example. So let's say you have two resistors in parallel, and one of them is 100 ohms, and the other one is 25. Let's find the equivalent resistance for that. Can we use this formula up here? We just divide, say 100 by 2? No, because they're different values. So what we do is we say REQ equals 1 over 100 plus 1 over 25. Now, some people might look at that and say, okay, that looks a little complicated. We'll just say that's 100 plus 25. But that's not the way that it works. Okay, you really have to do each one of these steps to figure this out. So let's do that. So this equals 1 divided by, so 1 over 100, that's 0.01, and 1 over 25 is 0.04. Okay? So if we do these, if we add these together, that's 1 over 0.05. And if we do that division, we see that that is 20 ohms. So that's the equivalent resistance of these two resistors in parallel. Okay? So again, notice that this equivalent resistance is less than either one of these resistors. Okay? That's always true for parallel resistance. The total resistance is less than the smallest value that you have in your circuit. Okay. Should I do one more of these examples? Yeah? All right. So let's say that we have two resistors in parallel.
If we make like 3 resistors.
Oh, 3 resistors. I don't know. It's getting kind of wild there. Are you sure?
Yeah.
All right. 3 resistors in parallel. Let's say that we have 3 kilo ohms there, and then 12 kilo ohms. Actually, yeah, let's make this. Yeah, sure, 3 kilo ohms, and then 1.2 kilo ohms, and 1.2 kilo ohms there. Okay. So we can do this equivalent resistance again. So can we use this formula up here?
For 12 maybe.
Yeah, maybe we could do that part over there. But since we got 3 of them in parallel and they're not all the same value, we might as well use this formula down here. So, so we can say that this REQ equals 1 over 3,000 plus 1 over 1,200 plus 1 over 1,200. So somebody's going to have to help me out with this. What is
500 ohms.
Okay, that's good. But that's a little farther ahead than I wanted to get just yet. So what is 1 over 3,000?
3.333.
Okay, so it's going to be 0.0 something, right? 0.033 or
3 zeros.
0.00333. All right, and then what's 1 over 1,200? 0.000833. And then one more of those, so 0.000833. So, so if I add these decimal numbers together, what do I get? Point 0.0019. So, yeah, essentially 0.002, right? Okay. And so then if I divide 1 by 0.002, what does that give me?
500.
Okay, perfect. 500. So that's the equivalent resistance for that circuit. It's 500 ohms. So if we had these three resistors in parallel, we would say that that's the same as just a single resistor that is 500 ohms. Again, this equivalent resistance is less than the smallest single resistor in our circuit. Okay? So, any questions about that? Okay. All right. So that's how we do equivalent resistance. If all the resistor values are the same, we can use this formula. If they are different, then we can use this formula down here. And no matter what, the equivalent resistance is going to be less than any single resistor in our circuit. Yeah?
Is there going to be problems where we don't know the value of one of the resistors?
There could be. So those kind of problems would involve current and voltage, though, and that'll be more like an Ohm's law calculation. So we'll talk about those next time. Yeah. Yeah. Other questions? Okay. All right. So then let's get on to the homework. So for homework, like I said, I'd like you to work on the calculator practice on pages 89 and 90 in your lab book. And yeah, this really is not very clear about exactly what numbers you're supposed to write down. So I definitely want to do an example of this so that we're all on the same page there. So let's take a look at what we have here. Okay. So this is called the calculator practice homework because we want you to get familiar with using your calculators for certain formulas when you're working with Ohm's law. Okay, especially when you're working with large or small numbers. So. So in your book, we've got a table that has a bunch of different columns. So there's value, exponent, and then, all right. We've got current. And that's got a value, an exponent, and then we have voltage or resistance here, and that also has a value and an exponent. And then we have voltage, which also has a value and exponent. And then we've got the metric result. So let me give you a little bit of background here. So so we've talked about how we can use prefixes like kilo, mega, giga, or milli, micro, nano, things like that, to write down really big or really small numbers without having to write out a whole bunch of zeros. But what about when you're using your calculator to do some math? If you see that you've got 2 giga ohms and you want to multiply that by something, well, giga stands for billion. That's 9 zeros. Do you still have to write out 2 and then followed by 9 zeros? No. So it turns out that your calculator has some shortcuts to help you get around that. So in particular, most calculators have a button that is labeled EE. And EE stands for times 10 to some power. So EE, it really means you're adding a bunch of zeros onto your number. So for instance, if you wanted to write 3,000, that's a 3 followed by 1 0, or I'm sorry, by 3 zeros. So you could write, you could just type it out, 3 and then 0, 0, 0, or you could write 3 and then you could push that EE button on your calculator and say 3. 3 followed by 3 zeros, okay? If you had, say, 4 mega ohms, mega stands for million, so you could write that 2 ways. You could write that 4 and then 6 zeros, or you could also write it as 4 and then just push that EE button again. 6, okay? 4 followed by 6 zeros. But what if you wanted to write really small numbers, like micro? So suppose you had 2 microamps. Well, micro is 10 to the minus 6th. That's what micro means. And that's all in that table in your book. So you could write this as 0.000002, or you could write 2 and then use that EE button again, and then minus 6, okay? Because we're multiplying by 10 to the minus 6th here. So this is how you can use your calculator to write really big or really small numbers. So this homework gives you a chance to practice that a little bit, okay? So for this homework, what we're doing is that we are using Ohm's law with big and small numbers, okay? So for this first problem, we're given a current of 2 microamps. So all right, so we have a current of 2 microamps, and then a resistance of 3 kilo ohms. And then we have to fill in everything else. So let's see how we could fill that in. So again, we're trying to use our calculator to do these calculations so we don't have to type in lots and lots of zeros. So what we can do is we can look at this, look at the 2 microamps, and try and figure out what micro stands for. So we have that, that super helpful chart. There's one on page 91. And if we look at that, we can see that micro stands for -6. So that's what we would fill in for the exponent here. We would say the exponent is -6. We just get that from this chart. We look at micro, and we see that that's 10 to the -6th. Okay, so we write that. And then,
What page was that?
there's a chart on page 91. It's a table that has what each prefix and then what power of 10 it is. So that's right after this homework. So then the next thing we can do is we can look at our resistance. We see 3 kiloohms. Well, we look at our chart again, we see that kilo is 10 to the 3rd. So the exponent is 3. So now what we can do is we can type this into our calculator. So when we type this into our calculator, we can use those that EE button that we talked about. So we're trying to find the voltage. So we're using Ohm's law here. So we say V, I, and R. We say V equals, we cover that up, we see it's I times R. So, so in this case, that would be 2 microamps times 3 kiloohms. So when we type this into our calculator, when we're typing in 2 microamps, what we do is we type in 2, and then we use that EE button. And then we type in our exponent. So that would be -6. And then times 3 kiloohms. So that would be 3. And then kilo is the power of 3. So we would say E3. And then when we hit equals, hopefully the calculator will give you back the answer in engineering notation. So you can put your calculator in a mode that will give you the answer in engineering notation. So the answer should be something like 6 times 10 to the -3. So then our value here would be 6. So we would write 6 up there. And then our exponent is -3. And so the metric result would be 6, and then -3 is milli. We get that from the table. So 6 milli, and then we're calculating voltage, so that would be 6 millivolts. Okay? So that's how we do that one. So are there questions about that? Let me do one more example where I actually show you on a piece of paper, okay? Okay, so this is the problem. So let's take a look at this next line down. So we've got 6 microamps, 4 kiloohms, and we want to figure out everything else, okay? So let's first of all figure out the exponent for micro. So what is the exponent for micro? Yep, -6. And then what is the exponent for kilo? 3. Perfect. So then, again, we're going to use Ohm's law here. So we say V equals I times R. And so, so the voltage would be 6 microamps times 4 kilo ohms. Okay? So when we put this into our calculator, let's see how we actually do this. Okay, so can you guys see the calculator?
Yeah.
All right. So what I'm going to do is I'm going to put in 6 microamps. So I put in 6, and then this calculator has an EE button. So if we look closely right here at this button, the button itself has this x to the -1, but above that there's this little spot that says EE. Can everybody see that right there? EE. And that's in blue. So if I want to use that, I have to use this blue second button first. So I push second and then EE. And if we look at the display, now that says 6 and then E. So now I come back to my exponent. So my exponent is -6. So for this, I have to make sure that I use the negative button that's all the way at the bottom of my calculator. So this negative button down there is what I use for the negative sign. So I push 6E and then -6. Okay? So that's 6E minus 6. So that's the 6 microamps. And then times 4 kilo ohms. So that'll be 4, and then second E, and then kilo is 3. So I would put 4E3. And then I hit enter. And so this gives me an answer that's 0.024. Okay? So that's fine. But what I'd like is I'd actually like that to come out in engineering notation. Hey guys, do you have a question back there? Doing all right? All right. So we want that to come out in engineering notation. So in order to do that, I have to put my calculator into engineering mode. So you can see up here there's a blue label that says Sci/Eng. So that allows me to switch modes. So I can hit second and then push that button to switch modes. So right now I'm in floating point mode, that's FLO. I can switch over to engineering mode and then hit equals. So when I do that, now I get my answers in engineering mode. So you can see this is 24, and then down there at the bottom, it says 24 times 10 to the -3. Okay, so that's what I would write for my value on my homework. So my value would be 24, and then my exponent would be -3. So then the metric result would be 24, and -3 is milli, so that would be millivolts. Okay? So that's how we can use our calculators to write really big and really small numbers, and we can do these things quickly without having to type in so many zeros. Yeah? What's that? A 20? Is that what you said? No. Okay. Okay.
Professor,
Yeah.
if it is just ohm, not anything, we just put a 0 or nothing.
Right. So yeah, if so we're talking about kilo ohms or microamps or things like that. If there was no prefix, then yeah, the exponent would be 0. That's right.
Do we have to round up if it's too big? For example, the last one,
The last one on this page, or
the next page,
okay.
exponent is 0.
So down here where yeah we've got volts and ohms. So yeah, let's do that one. So for that one, we have 200 and so here we're trying to find current. So we would write I equals V over R. So that in this case is 299 volts divided by 622 ohms. So then if we were typing that into the calculator, we would type in 299 divided by 622, and so that gives us 480. Yeah, so you could round that up to 481. 481, and then the calculator says times 10 to the minus 3. So the value would be 481, and then the exponent would be minus 3, and minus 3 stands for milli, so that would be 481 milli, and in this case we're finding current, so it would be milliamps. Yeah. So, yeah, questions about that?
Wait, so the 210, you times it or you minus it?
The what? The two tens?
The 210V? I don't know.
Okay. Okay. Yeah. So, yeah, if you have questions, I'll talk to you in just a minute about specifics. But yeah, are there other questions about the general procedure that we're doing here? Okay. All right. So that was an example of the homework. So then let's go on and do a preview of today's lab.
Can we write this 481 milliampere to 0.48 ampere?
Yeah, you could write it as 0.48 amps. That's another way to do it. That's fine. Yeah. Yeah, other questions? Okay, so then let's do a preview of today's lab. So the lab starts on page 75 today. All right, and so today's lab is going to be all in Multisim. So this first part says, using Ohm's law, select resistor values to obtain the currents that are listed in the table. So for here, we know that we have a voltage of 12 volts, and we want to get a current of 2 amps. So this is asking us to pick a resistor value that will give us that current. So we can use Ohm's law to do that. So we write R as V over I, so that's 12 volts over 2 amps. And that gives us a resistor value of 6 ohms. So we would pick a resistor of 6 ohms to give us that current. And then what we'll do is we'll simulate that in Multisim and see if our simulation matches our calculation. So we can open up Multisim here. Go. It starts on page 75. So we'll go to instructor files and then ET302, And then this is Ohm's law 2, parallel.
What's the name of it again?
The name of the lab
Yeah.
is Ohm's law 2 and parallel resistors lab. Mm-hmm. Okay, so this is the circuit that we're working with, and what we want is, we said we want to have 2 amps flowing through this circuit. And so we can measure the current up there. So when we run this, so we have a resistor set to 6 ohms. We've got 12 volts. So when we run this simulation, the simulation confirms that we have a current of 2 amps. So then we'd come back here to our lab and we would write down that our measured current is in fact 2 amps. And that confirms our calculation, okay? So we would do that for each of the values in this table here. So any questions about that? Okay, so that's the first part of the lab. And then second part is very similar, but you're having resistors or currents that are in the milliamp range. And then finally, we're going to get here and we're going to come to this part 1C, and we're going to have currents that are in the microamp range. Okay, so there is one tricky part about this this particular section of the lab. Okay, so let me illustrate what I mean. So let's look at this last part right down here for circuit 6. We've got a voltage of 20 volts, and we want a current of 20 microamps. So we want to find what resistance we would need. So we would write down the resistance is V over I, so that would be 20 volts over, yeah, so, yeah, so 20 volts over 20 microamps, and that would give a value of, well, okay, I take that back. Let's do this first one. So we got 20 volts over 1 microamp, and that gives me a resistance of 20 mega ohms, okay? So if I put in a resistance of 20 mega ohms, I expect to get a current of 1 microamp. Let's see what happens. So, so I can come here, I'll stop my simulation, I'll put in a voltage of 20 volts, and then a resistance of 20 mega ohms. I can just use that capital M to stand for mega. And then how much current do I expect to get?
2 mega.
2 micro.
Yeah, 1 microamp. I'm expecting to see 1 microamp here. Let's see what I get. I get 3.5 microamps. So that's not quite right. So what's happening is that there's a calculation error in this multisim program, all right? It has to do with the way that it calculates current. And so to get around this, we have to change something, the setting for this meter. So we click on the set button and we change the ammeter resistance. Right now you can see that it's 1 nano ohm. We're just going to make that 1 ohm. Okay? And now if we run that again, we get about 1 microamp like we expect. Okay? So you need to do that when you are doing this part 1C in the lab book, but only for part 1C. Okay? Don't do that for any of the other parts. And there's this note here. It says use the settings on the virtual DMM to set the ammeter resistance to 1 ohm. Okay? So do that only for part 1C. If you do that for any of the other parts, it's going to screw up your measurements on those parts. All right? So do this only for part 1C. So any questions about that? All right. So then let's go on to the next part of the lab. So for this part of the lab, let's open up the circuit that we have here. So this is circuit 10B. So we'll come back to our folder and open up circuit 10B. And you can see here we have a power supply and 2 resistors. And in the lab book, you are given, we say that we're supposed to have a battery voltage of 20 volts, that's fine. And then we need a voltage of 5 volts on one resistor and 15 volts on the second resistor. And then you have 3 things that you can fill in. So you can choose the current, the resistor 1, and resistor 2. So basically, because you only have 2 resistors and you have 3 things that you can choose, one of those things can just be picked arbitrarily. You can just choose, one of these 3 things. You can pick any value you want. And then once you pick that, you can use that to find the other values, okay? So what I do is I pick a value that makes this easy for me. So I usually pick a current of 1 amp. So I just choose, okay, I'm going to have 1 amp for my current, and then that makes these other calculations pretty easy. Okay? I know that I'm going to have 1 amp flowing through a resistor, and I'm going to have 2 volts on that resistor. So then we say that we want to figure out what that resistance is. So we use Ohm's law. We say R equals V over I. And here I have chosen, or I know my voltage for resistor 1 is 2 volts. So that's 2 volts. And then my current, I just picked that to be 1 amp. So 2 volts divided by 1 amp. So what's 2 divided by 1?
2.
2. That's exactly right. So we get 2 ohms. So that would be what I would pick for resistor 1. Would be 2 ohms. Okay? You could do the same thing for resistor 2. Here you would have R is 18 volts over 1 amp. So what's 18 divided by 1?
18.
18, exactly. So we'd have 18 ohms there. So if we pick those 2 values, then we should have 2 volts on the first resistor, 18 on the second one, and 1 amp altogether. So let's try that. So we'll make this one 2 ohms, and then the second one is 18 ohms. And now we can look at the voltages for each resistor and the current for the circuit. So if everything went well, then yeah, I should be seeing 2 volts, 18 volts, and 2 amps. Now, I'm going to try and run this, but if I look up here, right now all the run button is grayed out. I'm trying to click it, but I can't. It's not letting me do anything. And the reason for that is because another simulation is already running, and I can only run one simulation at once. So remember, I had this other simulation open and I ran it, and I guess I never stopped it. So if I want to run this new one, I have to go back to my first one and stop that. And then I can go to the second simulation, and now that run arrow is green again. So now I can run this one. So I run this, and sure enough, I get 2 volts on the first resistor, 18 on the second one, and 1 amp total, just like I wanted. Okay? So that's how we're going to do that part of the lab. Questions about that? All right. So then that brings us to the next part, and this is about parallel resistors. So this is just saying, okay, imagine I had a 1 ohm resistor in parallel with a 1 ohm resistor. What would be my equivalent calculated resistance for that?
2.
If they were in series, we would add them up and they'd be 2 ohms, but here they're in parallel. So how much resistance do I get?
2.
A half. Yeah, this is a half ohm. So this would be 0.5. Remember, when we have 2 resistors in parallel and they're the same value, the total resistance is just one of those divided by the number of resistors. So this would be 1 ohm divided by 2, so that gives me 0.5 ohms. And then there's a simulation for that. I'd run that in Multisim and check my measured resistance there and make sure that it matches my calculated resistance. So, questions about that? Yeah.
Would that same go as the other one too?
Go for which one?
The second one?
Yeah. So it's the same idea here. So here we have 2 ohms in parallel with 2 ohms. So what would be the equivalent resistance for that? 1, exactly. Yeah, you have 2 ohms divided by 2 resistors. That just gives you 1 ohm. And then you'd measure that. So same idea. And then the next section of the lab is the same idea again, but here we have 3 resistors in parallel. Okay, so you would calculate your value and then measure that and make sure that the 2 things matched up. And then down here you would find the resistance, and you would calculate the current. Okay, and check that against Multisim. And then that is the end of the lab. This is the first page of the next lab. So this is the last section for today on page 77. So any questions about that?
We didn't do the other page that you showed us.
So this will be the first page for next time.
Oh, okay.
Or have we done this one already? Not. I think that'll be the first page for next time. Yeah. Yeah. Other?
How did you do the 2B with the 3 resistance?
Okay. So for this one, what you have is you have 3 resistors in parallel, and they're all the same value. So you just take the one of those resistor values and divide it by 3. So in this case, that'll be 1,000 divided by 3 gives you about 333. Yeah. Yeah, other questions? Okay, then let me take attendance and then I'll let you go.